All right, we're switching gears. So the whole course has kind of led up to this point, kind of. A lot of the stuff that you learned up until now will be used in this chapter and the chapters going forward. So chapter 6 is rational expressions, functions, and equations, really. So the first thing is that something that is rational is something that can be written as a fraction. So I consider a rational expression something where there is a variable in the denominator. Now, this is an example of a rational function, which is defined as y as a function of x, where x is in an expression where there's an x in the denominator, right? So a rational expression, this is a rational expression, there's an x in the denominator, and then a rational function is y defined by a rational expression. And this is the graph of this rational function. So this is y equals x divided by x plus 3. And what I want you to notice is how the graph behaves around x equals negative 3. So I drew a dotted line here to show x equals negative 3. And you'll notice that the graph itself is the red graph. So as the red graph approaches this dotted blue line, it gets close to it, but it never quite reaches it. And same thing this way. You'll notice the graph gets close and close and closer and closer, but never actually reaches it. And that's because when you have an x in a denominator, there's things that x can't be because you're not allowed to divide by 0. So the reason why is that if I was to put negative 3 into my function, I'd have negative 3 divided by negative 3 plus 3, which would be 0 sorry, not 0, which would be negative 3, got excited there, negative 3 divided by 0, which is undefined. So you have to be careful when you're talking about anything that is rational in terms of x, that when you're looking at it, there's things that x won't be able to be, and it's anything that makes the denominator equal to 0. So this leads us to a conversation on domain. Domain is the possible values of x for every function that we talk about. So here we're going to be talking about the domain of these rational functions, and we're going to give it in set builder notation as well as interval notation. So when you're giving the domain of a rational function, it has nothing to do with the numerator. It's all about your denominator. You cannot divide by 0. So 5x squared cannot equal 0. And when you do this, then you're just solving an equation. Now this one's quadratic, but I could solve it by algebraically using the square root method. So I'm going to divide by 5, which will still stay 0. I'll take the square root and it'll still stay 0. So x cannot equal 0. So for this function, if I was putting in values for x, I could put in everything but 0. This is your set builder notation. If I wanted to do it a little bit more like proper, I'd say it's the set of x such that x is an element of the real number system but cannot equal 0. Interval notation, no one ever uses for domain, but the textbook loves interval notation, so we'll just write it a few times. Interval notation, instead of saying what x can't be, it's what it can be. So it can be everything from negative infinity up to 0, and then everything from 0 to infinity. So you just put round brackets for anything that x cannot equal. All right, let's look at this next one. So for this next one, again, it's just the denominator. X times 2x minus 1 cannot equal to 0. This is another quadratic equation. It's already been factored for you, so we're going to use the zero factor property to say that x cannot equal 0 and 2x minus 1 cannot equal 0. Which means that x cannot equal 0 and 2x cannot equal 1, right? I'm adding 1 to each side and then dividing 2 on each side, and I get x cannot equal 1/2. In set builder notation, I would just say that x cannot equal 0 or 1/2. And again, you could put the whole rest of the sentence if you want, but you don't need it. And then in interval notation, it's going to take a lot of room because you'd have to say it's everything from negative infinity to 0, from 0 to 1/2, and then from 1/2 to infinity, right? So interval notation, set notation for the domain of this rational function. Last couple here. In this one, again, it's the denominator that cannot equal 0. So we've got another quadratic that cannot equal 0, and this one's just not factored for you. So this is a trinomial. We're going to do the AC method. So the two numbers that multiply to give me -6 and add to give me -1 would be -3 and 2. Now, because it's a 1 in front, I don't have to do the whole AC. I could just put x minus 3, x plus 2 cannot equal 0. If you wanted to do the whole AC, please feel free, okay? But in chapter 6, you're going to be factoring so much that anytime there's a 1 in front, take the gift, okay? And then again, we're going to use the zero factor property to say that x cannot equal 3. Same thing here. Oh, I guess I should put the step in there. X minus 3 cannot equal 0, which I would solve by adding 3 to each side to get x cannot equal 3. And then same thing here, x plus 2 cannot equal 0. Minus 2 from each side, and I would get x cannot equal -2. So my domain in set builder notation would be that x cannot equal -2 or 3. And again, set notation is awesome. If I wanted to do interval notation, I'd say x can be everything from -infinity up to 2. And then from -2 to 3, and then from 3 to infinity. If it helps, you could draw yourself a number line and just put holes at -2 and 3 just to help guide you in your interval notation. Last one here, this again is my denominator. I haven't cared at all what's in the numerator. So for this one, 5 cannot equal 0. Well, what do you notice about that one? There's no x, right? And it's a contradictory statement, meaning there's no solutions. In other words, there is no restrictions in the domain, so it would be an element of the real number system or -infinity to infinity. This actually isn't a rational function. This is a linear function, right? There is no x in the denominator, so there is no restrictions on x. All right, go and practice finding the domain.